All right, you IBSL1 fans, we're back with 3.3, which is all about transformations of functions. Now, you guys might have some sort of knowledge of transformations already, so we're just going to kind of go over some basic transformations using parabolas. You guys should have seen these before. This is an example of a parabola. Parabola. Some common features of the parabola. This point that's at like the very top of the mountain or the very bottom of the valley, depending on its orientation, is called our vertex. And in general, we can call the vertex h comma k as some sort of coordinate. Every parabola has this vertical symmetry, or excuse me, horizontal symmetry. So there's always this line that goes through the middle of it, right here. And we are going to call this the axis of symmetry. So right here, axis of symmetry. Now, this particular parabola, this one over here, has been transformed. It's not like your typical parabola. A typical parabola we call the parent function. So that's a parabola that has not been transformed at all. Notice that the parent function equation is y equals x squared. It's the most basic parabola you can have, and it looks like this. It goes through the origin, point 0, 0, and it opens up. So we're going to use the parent function in a lot of these little transformation examples. But that's what each of them looks like, that it goes through the point 0, 0. That's its vertex. And the axis of symmetry is y is equal to 0. Remember, vertical lines, sorry, x is equal to 0. My bad. Vertical lines are x equals something. So, let's see. A reflection in the x-axis is going to be our first transformation that we're going to do. So I'm going to draw that in pink. The reflection in the x-axis, basically just think of it as folding itself over the x-axis. So just folding it in half vertically. So it would look something like this. Now, the equation for that is you put a negative on the outside of the function. So we're going to do y equals negative x squared. Please notice this negative is on the outside of the function. And that's going to come up a lot more later. So that was our first reflection. Now we're going to do a vertical stretch. So a vertical stretch is like, picture taking the entire graph and then just grabbing the top and the bottom and like pulling it away from this x-axis right here. So a vertical stretch would have essentially make this parabola skinnier. So it'd look like this. It would get stretched out more towards the top. The vertex would stay in the same place. It would still be 0, 0. Now, a possible equation for this, you just put like a scalar multiple on the outside of the function. So 2 times x squared. This is called a scalar multiple. There's lots of vertical stretches you can do. This is just an example. Now, you guys, the word translations. Translations in general do not change the shape of the parabola. They don't stretch it or squish it or anything like that. They just move it around. So, one example of a horizontal translation, let's say that this vertex of the parent function is at 0, 0. We could shift it to the right. So move the whole parabola over right here to, say, 3, 0. So that has been shifted to the right. It's a horizontal translation. We could also do a vertical translation. Let's do like a shift down on this one. No, we'll do a shift up. Let's say I took the whole parabola and shifted it up by 2 units. It would still have the same shape, but this point would be 0, 2. You know, it used to be 0, 0, but it got shifted up 2. Now, the interesting part of these translations is what the actual equations are. Now, notice how this parabola got shifted to the right 3 units. The most common mistake I will see is kids will say, oh yeah, I remember that it's like with the equation you put it inside, which is true. So it's going to be x3 to the right. But a lot of students will want to put a plus right here because that makes intuitive sense. Pluses usually go in a positive direction and not a negative direction. But you guys, when you're inside the function or when you're doing horizontal translations, it's actually backwards. The -3 would kick it 3 to the right. If I put a +3 right here, if I were to do this, that would actually move it to the left. So we are not going to do that. So let's make a note about this when you're inside the function. So inside is, I call it flippy floppy, where it goes backwards than the way you think it should. Negatives go positive, positives go negative. Yeah, it's like, you know, cats and dogs living together. It's like mass hysteria. Now, the vertical translation actually does work the way that you think that it should. So this is when a vertical translation is outside the function. So horizontal is inside, vertical translation is outside. So this is going to be y equals x squared plus 2. Now, please notice that the plus 2 actually did move it up 2. So this works the way that you think it should. Like positives go up, negatives go down. It's only when you're inside the function that it's this weird backwards relationship. So let's use all that knowledge to sketch a graph. When I look at this equation, sketch a graph of y equals x plus 3 squared minus 2. First of all, I started a graph with a little ghosty parent parabola here. But when we look at this equation, I see 2 transformations that have happened. There's a +3 inside and a -2 outside. So let's just list what that would do. The +3 inside moves the parabola 3 to the left. Remember, that's that flippy-floppy relationship, so it actually goes 3 to the left. Now the -2 outside, that works for the way you think it should. It moves it moves it 2 down. So the shape doesn't change. It doesn't reflect or flip or anything like that. It's just this point, 0, 0, is going to have to move 3 to the left. So 3 to the left and then 2 down. So here's our new vertex. It's been shifted 3 this way and 2 this way. So it would look something like this. Don't worry too much about your x-intercepts like being spot on. That'll come later. Right now I'm just more concerned with, like, does it open up the right way or open down? Does it shift left and right and up, down the right amount? That's all I'm concerned about. Next one, sketch a graph of g of x. Okay, so same thing again, but we have a couple different transformations going on here. I see a 2 being multiplied on the outside of the function, and I see a +3 also on the outside of the function. So, similar last time, this is going to be a vertical stretch by factor of 2. So that's because of this 2 on the outside right here that's getting vertically stretched. Then this +3, that is going to be a vertical translation of +3. So up 3. So the vertex was at 0, 0, and then it's going to get moved up 3. So 1, 2, 3. It is now here at 0, 3. Now, the vertical stretch part means that your parabola has gotten a little bit skinnier. So rather than this, you know, classic parent function shape, it'll be slightly skinnier. Don't worry too much about actual coordinates and stuff like that. Just make it look like it got vertically stretched a little bit. Last example, example 17. Let f of x equal x squared, the parent function. Describe a series of transformations which map f of x onto the graph of g of x. So we have to tell how this parabola got turned into this parabola. Then write an expression for function g of x. Well, when I look at this one right here, I see that it got horizontal translation of to the left of 4. So left 4 and a reflection in the x-axis. So if I start to write this equation, g of x, it's going to be flipped upside down, so there's a negative on the outside of the function, but then inside the function it went to the left 4. But remember, inside a function, it is backwards. It's flippy-floppy of how you want it to be. So left 4 is actually a plus 4 inside the function. Anything inside moves it left-right. Anything outside moves it up-down. When you're inside, it's backwards. When you're outside, it's straightforward. Same problem again. We need to tell how the parent function, y equals x squared, got turned into this. I see a couple things. Let's get zoomed here. I first see that it went to the right 3 and up 2. And that looks a little bit wider than the parent parabola. It looks like it's been vertically compressed. So that's actually a squish from the top and the bottom. You can tell that because, like, the classic parent parabola goes over 1, up 1 as its like first step, and it goes to the left 1, up 1. But if you look at this guy, if you go over 1, it goes up like a half. And over here, it goes left 1, up like a half as well. Now, I'm having to estimate because, like, there's no markings, but I'm pretty sure that they wanted that to be halfway in between. Also, if you look at it, if you go 2 steps out, it does go 2 steps up. So, let's see. The equation for this would be g of x is equal to... My thing here? No. Let me see. It didn't get flipped upside down, so it's just x minus 3. Remember, it's flippy-floppy. Squared, and then a plus 2 on the outside. Now, you guys, if I were to write this right now, I got the horizontal translation, I got the vertical translation, but what I didn't get is the horizontal compression. So, let's actually, here, take off this front part. This got compressed by a factor of 1/2. Because it took the graph from the top and the bottom and squished it by a factor of 1/2. You can tell that because as you go 1 step over, it goes a 1/2 step up. Instead of the parent equation, where if you go 1 step over, it goes 1 step up. So, that's my equation. In summary, you guys, a reflection in the x-axis is going to look like this. Y is equal to negative x squared. It's a negative on the outside of the function. A vertical translation is going to be y equals x squared plus k, where k, if k is positive, it moves it up. So k greater than 0, it goes up. K less than 0, down. Next up, a vertical stretch of a scale factor of absolute value of a. That is going to look like this. Y equals ax squared, where that scalar is being multiplied on the outside. Now, the reason that they add these guys right here, the absolute values, is because when a is negative, there's also a reflection in the x-axis. But we're trying to separate those two, so they're just talking about the absolute value of a. When that absolute value of a is bigger than 1, like 2, 3, 4, 187, that is a vertical stretch. But when it's in between 0 and 1, like 1/2, 1/3, 4/7, something like that. That is going to be vertical compression. That's a squish from the top and bottom. All right, you guys, that is going to do it for the day. We will continue transformation